Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. This lesson actually begins our unit on circles. And while we've talked a little bit about circles, we've talked about area, circumference, stuff like that, there's a whole nother section of topics that deal with circles, and that's what this unit is going to cover. So to begin, we are going to skip the do now, and we're going to just jump right into the vocab of circles. So a circle, it's a set of all points in a plane that are equidistant from a given point. That point would be the center of our circle. Let's kind of sketch an example of what that means. That means if you take a point, just plot a point, and you choose a distance. Oh, let's choose 1 inch. Right, so you extend 1 inch away from that point, and you're going to do that in all directions. Right, and there's an infinite amount of segments I can draw here. But the idea is if you put a point at the end of each of those segments, all of those points combined would create our circle. And again, all of those would be exactly 1 inch. So you'd have a perfect circle if I could draw perfectly. The interior of a circle is the set of all points inside the circle. Exterior of a circle, the set of all points outside. A chord is a segment whose endpoints lie on the circle. So you can see a chord down here, chord AB. The endpoints are on the circle, and they are connected by a segment. That would be a chord. A secant is essentially a chord that's extended to be a line. So a secant is a line that intersects the circle at 2 points. But you can basically think of a secant as a chord that is a line. Right? A chord is a segment, but if you had changed the segment to a line, you would then have a secant. A tangent is a line that intersects the circle in exactly 1 point. And the point of tangency is the point at which a tangent line intersects the circle. Let's go down to this diagram so we can just see all of them right here, all of the different pieces. We already talked about a chord, a secant. Again, it's a line that intersects the circle in 2 points. And a tangent is a line that intersects the circle just once. So those are the vocab words you need to be familiar with as we move forward with the rest of this unit. And we'll add some more here and there as we go. Let's look at the second page. For this one, you're just going to identify the following parts of the circle: chords, tangent, radii, secant, diameter. We didn't cover diameter and radii up above. That's just because those should be familiar to you. A radius, radii is just the plural form. A radius is a segment that goes from the center of the circle to the circle. Right, so that would be a radius. This would be a radius. This would be a radius, etc. A diameter is a chord that goes through the center of the circle. So a diameter is a special type of chord. It's one that goes through the center of the circle, and that's what I just drew in blue up there, whereas the red segments are the radii. Okay, so identify as many of these as you can. As many chords as you can, as many tangents, radii, secant, etc. And then, so you're going to pause the video and then come join us for a discussion once you have your answers down. Okay, so there's actually 2 chords here. There is chord CB, segment CB, and there's also chord EF. Now you may think, Mr. Fawcett, that EF part of the diagram is a line. Well, it can be a line, but you could also just look at the segment going from E to F, right? And if we just looked at the segment from EF, or segment EF, then it would be considered a chord. Let's do secants because they're similar to chords. All right, there is only one secant here, and that is line EF. Right? Because I can treat EF as both a segment and a line. It just depends on, do I want to only take a portion of that line, which would make it a segment, or do I want to include the whole line, which would make it a secant? Now, we could not say line CB. Right? Line CB is not existent on the diagram. There are no arrows coming off of the sides of the segment. Right? So whereas EF, you could use that as either a segment or a line because it does have the arrows, and you can always, if you just take a portion of a line, that's going to be a segment. You can't do that with CB, right? Because CB is only a segment on the diagram. We are not shown that it extends to infinity on both, or indefinitely on both directions. So the only secant here, line EB. Let's go to tangent. Only one tangent here, and that's line L. Right here. There are two radii. There's radii AC and radii AB. And if I combine both of those, that would give us diameter BC or CB. Okay, let's keep moving on. We're going to talk about pairs of circles. Circles are congruent if and only if they have congruent radii. So if two circles have the same radius, we know that they will be congruent. We will be able to prove that. Circles are concentric if and only if they are coplanar and have the same center. Let's break this down a little bit. So concentric, if they are coplanar, which means they lie in the same plane, and they have the same center. So you may think, well, why do we have to say the coplanar part? Well, because I could, let's say I have two circles with center, we'll just call that center X. So we have one circle like this. But then let's say the other circle is not in the same plane. You may think, what would that look like? Maybe it would look something like this. You could think about, what if you spun that red circle around that center, or think about the circle coming out of the page at you rather than lying flat on the page or on the screen. So they have to be coplanar. They'd have to, you'd have to be able to place the circles on the same sheet of paper, and they would have to have the same center for us to consider them concentric. Circles are tangent if and only if they intersect in exactly, well, think about what a tangent line on a circle represents. It intersects a circle once. Tangent circles intersect each other in exactly one point. So if we come over here, those two circles intersect there. These two circles intersect here. It's possible to have internally tangent circles. That's where one circle lies completely within another. And externally tangent circles, that's where one circle lies completely outside the other, again, except for that point of tangency. Number 4, a common tangent is a line that is tangent to two circles. So if we just take line L here, right, line L is tangent to both circle A as well as circle B. That's what they mean by common tangent. Now, you can have tangents that are called internal tangents. These are tangents where the circles lie on opposite sides of the tangent. Whoops. And you can have external tangents where circles lie on the same side. So based off of those definitions, and we'll just call this diagram 1, diagram 2, do we think diagram 1 is an example of internal tangents, or do we think it's an example of external tangents? Same with diagram 2. Pause the video, take a few seconds to think. Which one represents internal, which one represents external? And you can actually just do it by lines down here, L, M, P, Q. Well, line L, right? Line L, the circles are both on the bottom side of line L. So that makes line L an external tangent. Same with line M. So line L and M, these are external tangents because the circles lie on the same side of these lines. Whereas tangents P and Q, the circles lie on opposite sides of those lines. And again, you're just looking at one line at a time. Right, so if I look at line P, the circles are on opposite sides of that line. That makes line P an internal tangent. Same with line P or line Q. All right. I know it's a vocab heavy day, and now we're going to touch on 2 theorems before we move on to some application problems. Although, yeah, we'll get to one at least, and then we may do a proof as well. Okay, so our first theorem says, and we'll do this is the one at the top. Looking at this one up here. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So if I have a tangent line, like line L here, it's going to be perpendicular to the radius that intersects the point of tangency. So it's not perpendicular to every radius, it's just perpendicular to the radius that intersects the point of tangency. Likewise, if a line is perpendicular to the radius of a circle at a point on the circle, then the line is a tangent to the circle. So this is the converse of that theorem above. You'll notice that this, in diagrams, right, this is useful because it may create a right triangle for us. Right? If we know 2 things are perpendicular, we can put a right angle there. And if we know that there's a right angle there, we may have some right triangles, and then that opens up a plethora of different theorems. Right? We can use Pythagorean theorem. Any triangle, right? We can use the triangle sum theorem. But then we can also use our sine, cosine, and tangent. I know we do have, we are able to use trig with non-right triangles, but generally, right, when we're using sine, cosine, tangent, we're focused on right triangles, so SOHCAHTOA. Our next theorem says that if 2 segments are tangent to a circle from the same external point, then the segments are congruent. So actually, let me give you a new diagram here. I need to do a circle, so I'm going to not need my segment tool. So let's say I have a circle here, and I just pick a point outside the circle here. Well, if I draw 2 tangents from this point to the circle, and I label the point of tangency, well, then I know that segment AB is congruent to segment AC. So 2 tangents drawn from the same point are going to be congruent to one another. All right, let's at least apply these to one problem. And let's see, which one do we want to do? Let's actually do one of the more challenging ones. Let's do number 4. So it says segment PR and PS are both tangent to circle Q at points R and S respectively. And we need to find the measurement of angle Q. Well, may not seem like we're given a lot, right? We're given an angle and we're told that PR and PS, those segments are congruent. Take a moment to pause the video and see if you can find a way to figure out the measurement of angle Q. There's a couple different ways you can do this, and maybe we'll talk about both of them, but I don't want to give you too many hints because I think you have the ability to figure this out. It just may not be very clear right away. So pause the video, take some time to think about it, and then come join us for a discussion. Okay, so maybe you notice that we should have some right angles here at R and S, and that goes to one of our theorems up above. A tangent line will be perpendicular to the radii at the point of tangency. Now, right now, we have enough information to figure out the measurement of angle Q. This will go back to our the interior sum of polygons, right? I forget exactly what unit we learned this in, but we have a formula for figuring out how many degrees the interior angles of convex polygons should add up to. And we know that for triangles, it has to be 180. I think you probably know what it is for quadrilaterals, right? And this is a quadrilateral, 4 sides. It should add up to, all the angles should add up to 360. But if you forget, remember it's going to be 180 times a quantity n minus 2, where n is the number of sides. So if I substitute in 4 there, right, I get 180 times the quantity 4 minus 2, 180 times 2, that gives me my 360. So I know what 3 of the angles are. The only one I don't know is the measurement of angle Q. So the measurement of angle Q plus 90 plus 90 plus 42, that has to be equal to 360. And if I do some simple inverse operations, I'm going to get the measurement of angle Q is equal to 138 degrees. Measurement of angle Q is equal to 138 degrees. Now, I definitely think that's the easiest way as far as number of steps go. But some of you maybe created some triangles here. All right, so let's go back and look at how we could do it. Creating triangles. Hopefully we get 138. So if I split this quadrilateral down the center, that gives me 2 actually congruent triangles here, right? We could prove this congruent by HL. They both share the hypotenuse. Oops, there we go. They both have congruent leg. They each have a congruent leg, and they both have a right angle. So if they are congruent triangles, well, they both have a 90-degree angle. We know that both of these angles right here must add to 42, but since they're congruent triangles, both of these angles will just be 21 degrees, right? Half of 42. So you could then find, I'll just call this x, 1/2 of q. So I could have x plus 90 plus 21 equals 180. Right? X is then equal to 69. And because these triangles are congruent, well, this bottom angle also has to be equal to x. So the measurement of angle Q is equal to 2 times x, which is equal to 2 times 69, which is equal to 138 degrees. Same thing that we got before. It's always good to know how to approach a problem a variety of ways. It shows you really understand all the math that's going on here. I think we're going to end with the proof. Okay, so it says given segment AB and AC are tangent to circle P at points B and C, respectively, we want to prove that AB is equal to AC. So we're proving one of our theorems above, right? If we have 2 tangents drawn from the same point, right, drawn from point A, then we know that those tangents will be congruent or that they'll be equal. Either one basically means the same thing. And I give you a little asterisk. It says you may use the property that tangents are perpendicular to the radii of a circle. So that's our first theorem from up above. We should actually say at the point of tangency, just to make sure we're clear. And it says use congruent triangles in CP/CTC to prove this theorem. Okay, read through the proof. See if you can come up with the correct reasons. You may have to draw some extra segments or some angle arcs or congruent tick marks in your diagram to help keep track of everything. But once you think you have an idea of what those blanks are, then join us for one final discussion. Okay, so the first one is obviously given. We are told that. Then we're asked to figure out why segment AB is perpendicular to segment PB, and segment PB is not drawn, so we should go ahead and draw that in. Let me recenter this actually. I'm going to draw PB in. I'm actually going to draw PC in because we're going to need that as well. So why are they perpendicular? Well, that goes back to this reason, right? It's our first theorem from up above. Tangents are perpendicular to the radii of a circle at a point of tangency. If we know that segments are perpendicular, well, what does that tell us? Well, it tells us they have a right angle, but more specifically, it tells us that that angle has a measurement of 90 degrees. So we've proved the segment's similar. Now we've proved the segment's perpendicular. Now we know that they form angles that are 90-degree angles. And this is just the definition of perpendicular. Can I get through this proof without a spelling mistake? We'll see. Then it says PB is congruent to PC. PB is congruent to PC. You may not know this one because this is the first time we're using it. But all the radii of a circle are going to be congruent. This actually goes back to the definition of a circle. Right? We form a circle by drawing an infinite amount of radii and attaching points at the end. So the way we say this, oh, there's my spelling mistake. Radii of a circle are congruent. Again, a new one, so if you didn't have this exactly, that's okay. Then we're told that PA is congruent to PA. Well, I guess I better draw that in. Segment PA. Anything congruent to itself that's going to deal with the reflexive property of congruence. Let's put a tick mark there. And now, how do we know that PBA, that's the triangle in blue, how do we know that that is congruent to PCA, triangle in pink? Well, that's going to be HL congruence, right? They both have a right angle. The hypotenuse hypotenuses are congruent, and a set of legs are congruent. Once I prove the triangle is congruent, I should then be able to say that AB is congruent to AC. That's going to be CP/CTC. Corresponding parts of congruent triangles are congruent. And then if I know that two segments are congruent, I can say that they are equal in measurement by definition of congruent segments. And now I've proved what I was trying to prove at the top. AB is equal to AC. And again, this was a proof of our second theorem up above. Let me just show you real quick, make sure we're on the same page. This one right here. So if we have two tangents drawn from the same point, then the tangents will be congruent or equal in measurement. That's going to do it for this video. We'll look at some more application problems in class, but you definitely want to make sure you understand the vocab and you understand what these two theorems are saying. Those are going to continue to pop up throughout this unit. As always, enjoy the rest of your day, and we will look forward to seeing you next time.